Okay, before I forget. Just two. November 2nd. You think that's a Wednesday? I could do it the Monday, I don't really care, but it has to be that week. So if some of you had the exams on that same day, I could change it to Monday. But that's when the test is due online. Remember how I told you to study? It's already online. We haven't yet covered all the topics, but we're going to jump into another one. We're going to jump into the chain rule. Last time we did the product and the quotient rules. How to differentiate products and quotients. Okay, so first let's recall. Definition. What's this? Okay, and what's the derivative of x to the n? Or if I have the derivative of a sum of functions. So this is the derivative of f plus or minus the derivative g. Just differentiate one at a time. Okay, what if I have the derivative of a product of functions? F times g.
First one.
F times g prime. By the way, side note, let me tell you that something. I don't think there's ever going to be a case where you'll use it, so never mind. How to differentiate that? Those should all be in your head. And not only should the formulas be in your head, you should know actually how to apply them. Know when to recognize you have a multiplication or a division or something else. Okay. So right now we're going to jump into another derivative technique that allows us to take derivatives of different kinds of functions. First of all, let me remember what. I did do that example with you guys about the yeah, so I think we're good. Okay, so now we're going to move on to 3.4. It's called the chain rule. Suppose we wanted to differentiate this guy, find the derivative of x squared plus 1 squared. Right? Now, based on what we know so far, we kind of have a couple options here. One, I could just expand this guy. Right? I get x to the 4th plus 2x squared plus 1. Right? And then I just do the power rule on each individual term. Right? So I would get 4x cubed plus 4x. Right? Another option would be, I could think of this as just the derivative of x squared plus 1 times x squared plus 1, and look at it as a product rule, right? This is f, and that's my g, and I just go through that rule. Okay, not so bad, right? So this guy, not so horrible. But what about this guy? Now things get interesting, right? 20th power. There's no way I'm going to want to multiply that out. I'm not going to FOIL 20 things, right? And also, to do the product rule, that would also be crazy. I have 20 terms to multiply together doing the product rule in each term. That is kind of crazy, right? So how do we deal with this? When using one of our basic rules just doesn't work. The answer is called the chain rule. The chain rule allows us to differentiate. And by the way, remember this answer. We're going to do it. You're writing this down. Well, we're going to come back to the answer. I just multiplied this out. 2x squared plus 1. The answer is called the chain rule. This is a rule we use to differentiate composite functions. Functions inside of functions, right? Which we sort of did some stuff with earlier. But basically the rule says the following. The derivative of f of g, right? So this is a composite function, right? We have one function plugged into another function. In fact, remember when we were doing the inverse of composite functions way earlier in the semester, where we can sort of look at this as if there was an inside function and an outside function. You can kind of see that there's an outside function raising to the 20th power, but I took another function and put it inside it, right? So it's like this is your inside function. That's like the g. And there's the f is the power function. That's the outside function, right? So it says whenever you're differentiating something like this is how you do it. You differentiate the outside functions, leaving the inside function alone, and then you multiply by the derivative of the inside function. Derivative of the outside times the derivative of the inside, right? Where you leave the inside intact in the first one. Right? Now this is a very important rule, super important rule. The proof for it is kind of subtle, so I'm not going to actually prove it to you, but that's just something you should know. This is used to differentiate composite functions. Functions inside of functions. Basically, you look at all the rules that we've had, the basic rules like the power rule, ln and e to the x, and pretty much if it's not just an x, you need the chain rule. I should probably write that down. So it's kind of recognizing that form. What do I actually mean by that? For example, right? So if I ask you to find the derivative of x to the 20th, that's no problem. That's just a power rule, because it's just x to the 20th, right? However, as I did here, I asked you to find this to the 20th, right? It's not just x to the 20th. There's a whole mess of things raised to the 20th. Or if I ask you to differentiate e to the x, that's just a basic rule. The derivative is e to the x. It's different if I ask you to differentiate e to the x squared, or to differentiate e to the 2x, right? Because there's not just an x anymore, right? The rules only apply if it's just an x plugged into the function. If there's anything else, it's considered a composite function, where the inside function is the guy that replaced the x in the basic rule, right? And so whenever you have anything that complicated, this is how you're going to differentiate it. So this is something that we know now. And let's actually use it to differentiate that last example I had. Anyone want to take a crack at it?
x squared plus 1. Power 19.
Right, so what they just did was the power rule, right? The power rule says you take the power, you bring it down in front, subtract 1, but you leave the inside alone, right? Don't do anything with the inside yet, right? This is differentiating the outside function. Then you're going to multiply by the derivative of the inside function. Derivative of this is just 2x. Derivative of that is just 0, right? Now be careful, if your derivative has several terms, you need parentheses here, right? So you can even just put a parenthesis just to be safe. Right, because if there are several terms, you'd have to distribute them, right? Yeah, but that's basically the answer. And I can simplify this a little bit. I can take this 2x times this 20, and got 40x times x squared plus 1 to 19. And that is the derivative of this guy. This is the function that will give me the slope of that guy. Let's do one that we already know the answer for, just to, convince ourselves. So this previous example we already knew about. X squared plus 1 squared. The answer was supposed to give us what word? I forgot what it was. Anyway, so the chain rule says you're going to do what?
2.
Leave the inside alone. Times 2x. In other words, that's 4x times x squared plus 1, which is 4x cubed plus 4x, which is exactly what we got last time. Right? So this rule actually works. Right? So basically, this is the rule that you use when you don't just have an x like your basic rule says. Whenever you have one function plugged inside of another function, whenever you have anything that looks like f of g of x, and your g is not just x, g is something else that could be crazy. Then you need what's called the chain rule. So let's actually do some more. Oh, well, let's do that one that I mentioned earlier. The derivative of e to the x squared. Or the derivative of e to the 2x. Let's go here. What's this guy? So the chain rule says differentiate the outer function first, which is just e to something. Now what's the derivative of e to the x? It's just itself, right? So derivative of the outside function is just to copy back the old function. But now we have to multiply by the derivative of the inside. And what's our inside function here? The inside function is the x squared. That's the guy that's plugged in instead of x. So the derivative of that is 2x. So the derivative of e to the x squared is just 2x e to the x squared. Or this guy. Derivative of the outside.
E to the x.
Right. It's just the whole guy.
Times 2.
Then you multiply by the 2, which is the derivative of the power. What's this? Now it's fine.
So, Jhevon,
Yep.
the x becomes 0.
What becomes 0?
The x.
No, derivative of x is the 1. The 1 became 0.
Okay.
So that's the answer.
Can you do that first one?
By the way, what?
Can you do that first one? Very first
This one. Yeah, so I have e to something, right? So the outside function is the exponential. Now I know the derivative of exponential is just itself, right? The derivative of e to the x is just e to the x. Right, so if I'm differentiating the outside function, I literally don't do anything. So that gives me this. But then the chain rule says I have to multiply by derivative of the inside function. The inside function now is the x squared. That's the guy that I plugged in instead of the x. Right? So it's like my f is e to the x and my g is x squared. I took this function and plugged into that function. So derivative of e is just itself, but because it's not just an x, I have to multiply by the derivative of the power. In fact, we can make a general rule about that, which I recommend that you do. I'm going to require that you memorize this. This is the chain rule version of the exponential rule. This is e to the u, right? Where u represents any function of x. U can be anything. It doesn't have to just be x. But the answer is going to be u prime times e to the u. This is the derivative of e with the chain rule built into it. Know this. So now we know that to differentiate an exponential, it's going to be the derivative of the power times the original function. And notice that your old rule, the one you had memorized before, still applies, right? Because if I do derivative of e to the x, I can just take the derivative of the power, which is 1, times the original function. I still get e to the x, right? So this rule even supersedes the first one I gave you. This it's far more general, and this u can represent anything. Right? So every time you have an exponential function, the derivative is going to be the derivative of the power times the original function. Derivative of the power times the original function. Derivative of the power times the original function. That's always what it's going to look like for an exponential. What about this one? What's the derivative of ln?
1 over x.
Derivative ln x equals
1 over x.
1 over x. So that's the basic rule. That's what we get if it's just an x by itself, but it's not. So how do we do that? What do we do here?
1 over the...
1 over that whole thing. And you multiply by the derivative of that thing.
3x.
Parentheses. Right. Or in other words, I can write that as 3x squared plus 2 over x cubed plus 2x plus 1. This gives us another general rule for the logarithm. To differentiate ln of u, the answer is going to be u prime divided by u. That's the chain rule version of the log derivative formula. Right? To differentiate log of something is the derivative of the thing over the thing itself. And again, this would work even if it's just an x, right? Derivative of x would be 1, you still get back your 1 over x. What about this one? What formula applies here? Right, tell me the basic formula we know so far for that situation. Huh?
F prime, G prime.
No, the general formula.
3 x.
No, not for this. Forget. Tell me the general formula that you would think of applying to that. It's not that one. Why can't it be that? It's not that one. Why is it that one? This is an E. This is a 3. They're two different things.
2 to the x ln 2.
Would it be the power rule? Would that be what I apply?
No.
No. Why not? That's an x, the top is a constant. Here the base is a constant, the power is a variable, so it's not the power rule. What rule applies to that?
2 to
The
the
A to
x
the
ln
X.
x2.
It's the a to the x, right? That's the one that says the base is a constant, the power is a variable. What should the derivative be?
A
A
x
and X.
ln
Okay, so that's the basic rule that we have that would apply to this. The problem is here we don't just have an x, we have an x squared, but we know how to deal with that now because of the chain. But the first thing you need to know is when you look at it, you need to recognize what rule you should be using to apply to that. So derivative of the outside is going to be what? What do? You copy the same thing, then you put ln of the base. Copy the same thing, ln of the base. But then we have to apply the chain rule, which says multiply by the derivative of the inside function. In other words, this is going to be 2x times 3 to the x squared. And in fact, we can generalize this rule then. The derivative of a to the u is u prime a to the u of element a. So this is what I mean. A part of your study is not just memorizing the formulas. You need to know which one, when to apply which one, right? And if you have a specific number in a formula, it means it has to be that number. I can't just apply it anywhere I feel like. More examples. Okay. Start over here. What do we do? Right? There's no rule where there's a radical in it. All my rules have powers, so I'm going to rewrite this to look like something with a power. Now what? Right. Now it's a power rule. Notice that there's an inside function plugged into a power, so let's do the power rule. Minus a half. No. And then minus 2. Which the 2 can cancel this 2. And you have minus x times 2 minus x squared minus half.
So I have a question. So the minus 2 is from the x squared?
Yeah, it's a minus x squared.
Okay.
It's minus 2x is the derivative of minus x squared. And I cancel these 2's and got that. What about this one?
To the top.
So you want to do the product rule, I guess? I'd probably do the quotient rule, but you could also do that and do the product rule. I see this as just a division, right? This is f, that's g. So I know the derivative is going to be f prime times g minus f times g prime over g squared. F prime is the derivative of this, which is 1 times g, which is this guy, minus f, which is that guy, times g prime, derivative of this. How do I find derivative of this? Chain rule, right? Because it's a whole thing raised to the 16th. So I bring the power down, leave the inside alone, subtract 1 from the power, and multiply by the derivative of the inside, which happens to be 1. So divided by x plus 4 to what power? Huh? 32. Now what? Factor out. X plus 4 is a common term. I can pull that out. What power do I pull out?
15.
Pull out the smallest power. What do I have left over? Right, because I had 16 factors, I pulled out 15, so there's one factor left, just x plus 4 minus x plus 1 times the 16, and that's it. So this goes into that, how many times? That's 17. And so now I can simplify it here. This is x minus 16x. So it's minus 15x. This is 4 minus 16 minus 12 over x plus 4 to the 17. What about this one? What rule? Quotient rule again, right? There's an f. That's your g. So it's a division of functions. And so I know I'm applying this rule. So it's f prime, which is 1 times the g minus the f times g prime. How do I find that?
X to the third. Times
3x squared, right? Derivative of the power times the original function, chain rule. Divided by e to the x cubed squared, right? Or you can write it as e to the 2x cubed. And now what? E to the x is a common term in the power. I can factor that out. E to the x cubed. I do that over 1 minus 3x cubed over e to the x cubed squared. So this cancels that. So that 1 minus 3x cubed over e to the x cubed. What rule? Product rule, right? I have two functions. That's my f, that's my g. I have two things multiplying each other. So the derivative is going to be f prime times g plus f times g prime. F prime, how do I find the derivative of that? Chain rule. Okay, what happens? So times 2, which is the derivative of the inside, times
2x plus, oh,
times g plus
2x plus 5
times. What's that? Simplify. Or the common terms. This is a common term in both. This is a common square root plus in both. 2 is a common term as well. Just pull those up. 2 times 2x plus 1 times x squared plus 1. The power, what's the power of this one? Well, the 7th power. Well, the 4th power. What do I have left over? 8. No, this whole thing came out. The 2 came out as well. Right, so I have 4 factors I factored out. There were 5, so there's 1 left over inside here. Plus, right, there were 8 factors. I pull out 7, so there's 1 factor left. Times 5, I didn't do anything. Right, this I factored out, and so the 2 I factored out, and the x is just left. So now we can simplify. Here, this would give me 8x squared. This gives me 10x squared. It's 18x squared plus 8 plus 5x. That's the answer. Questions? How did I do that one? Closure rule. I have one function, which is my f, divided by another function, which is my g. I know the derivative should be f prime times g minus f times g prime over g squared. Just plug in the pieces. F prime, I have to differentiate this, which I need. The chain rule. X plus 1 to the 7 times 2 times my g, which is just this guy, minus the f, 2x plus 1 to the 8 times the g prime, which is 5 times x squared plus 1 to the 4th times 2x, all over this squared, x squared plus 1 to the 10. So now, again, just try to simplify. Very simplify these fractions. You factor the numerator and denominator so you can cancel stuff. It's not a complex fraction, so it didn't need to multiply it by LCD. So all we're going to do is factor all the common terms again. So we have the same guys. It's very similar to that, except we have a minus here instead of a plus. So we're going to pull out exactly the same thing. 2 times 2x plus 1 to the 7 times x squared plus 1 to the 4th. And we would have left over 8 x squared plus 1. This time it's a minus instead of a plus. 2x plus 1 times 5 times x. All of that is over x squared plus 1 to the 10. Now there's only multiplication I can cancel. This is with the 6th power. So we have 2 times 2x plus 1 to the 7th times. I have 8x squared minus 10x squared plus 8 minus 5x. And that's the answer. Questions? Yes? No? Did I say something funny? Just like laughing. So I guess you're starting to see why we need algebra for this game, right? If you look at something like this, you'll notice that problem 1A on your first test was a fraction that looked kind of like that. It actually came from the quotient rule. Right? So it is something that you're going to need to know how to deal with. Why do you need to simplify? Why can't we just stop here? Right? Yeah, that's what you're going to ask. Because later, when we're going to do things with derivatives, we're going to need to know when it's positive, when it's negative, which would involve knowing when it's 0. To figure out when it's 0, you need to factor it so that you can set each factor equal to 0. So you need to be able to simplify in order to do that, in order to do other things, to figure out where it's increasing, decreasing. To analyze the function, you're going to need to be able to simplify the function, and its derivative, and its second derivative, and so on and so forth. So, yeah, we're going to need algebra.
Wait, so
yes.
on an exam, this would just be one part of one problem?
Yeah, I could put that as one part of one problem. Right, so on the exam, like probably not problem 1, but like problem 2, it would probably have like 4 parts, A, B, C, D, maybe 5 parts, and each of them would be a derivative. Which is typical. If you go to the review, you'll see that it's a typical kind of problem. Anyway. That's pretty much the chain rule in a nutshell. It's pretty much going over the basic rules we have, except now we're dealing with things where we don't just have an x and something we're doing. We're like have this whole function plugged in. You have composite functions. So whenever you have functions plugged inside of functions and you want to differentiate that, you use the chain rule. There are other situations that we're going to need to know about though. So that brings us to 3.5, where we're going to talk about implicit differentiation. And logarithmic differentiation. So differentiating isn't hard enough, so we're just going to throw logs in there just to confuse everybody. Even if a log wasn't there in the first place, now we're going to throw it in, just to spice things up. Were you still copying? Wait, faster. Try to solve me the question. What was that? 8 x squared plus 1 if that was g, that was f. I know that this would be f prime g minus f prime g prime over g squared, which gave me 8 times 2x plus 1. 2 times 2x plus 1, 7 times x squared plus 1. Why do we need more kinds of differentiation? Well, let's explain. turns out we can define a function both explicitly and implicitly, right? Explicitly is how we've always been defining it, right? So it's the one you're kind of used to. So when you talk about an explicit way to define a function, it's not rated R or anything, it just means you have y is equal to f of x, right? Where your y is by itself, and on the other side, you have a function with x as the only variable. Or it could be a constant function, which you won't see it. But if a variable appears, it would be an x, only variable that appears. Right? So these are the guys who actually know how to deal with. Based on what f looks like, I know how to find a derivative, so that's not a problem. The explicit case is what we've been dealing with the whole time. There's so-called an implicit case, though. Implicit means y is not explicitly out in the open, it's kind of hiding inside a function, or inside the definition. So here's an implicit. It basically means you have a function with x's and y's mixed up. X's and y's are mixed up in the function definition. And you cannot solve for y. Or it could also be the case you don't want to. And I'll show you a case where you probably wouldn't want to. Right, so examples of this is guys like you've been familiar with y equals x squared, or y equals x plus 1, or x plus 2. Anything that looks like that, as you say, it's an explicitly defined function. When I talk about implicitly defined function, I'm talking about guys like this. They can look very simple, from like x times y equals 1, or x squared y plus 2xy equals 7x, or radical of xy plus 3y cubed times 4 equals ln x plus 2. So here I'm giving you an expression. The x's and y's are jumbled together. Right? It's not like I have y equals some function of x and I just apply the power rule. No, I can't do that. Here my y is mixed up with the x's, right? My independent variables and my dependent variables, they're entangled. Whenever I have something like that, I call it an implicitly defined function. A circle is an example also of an implicitly defined function, right? Like if I have x squared plus y squared equals 4, my x's and y's are kind of mixed up, and solving for y, I probably wouldn't want to do that. But so that's the idea. So I have this situation, but I'm still going to want to be able to find a derivative. What if I still want to find y prime? Right? How do I do it in that case? Well, we do what's called implicit differentiation. By the way, this takes advantage of the chain of Let's illustrate. Differentiate the following expressions. So here's the function, and I want you to find its derivative. function y, or the function x times y, or the function y squared. Start out slow and then we'll make it more complicated. Okay. So this is just an expression, y by itself. How do I find its derivative? It's really just y prime, right? Derivative of y is y prime. What about here? I take an x and I multiply it by the y. Now what? Huh? All the old rules apply, right? So it's not like just forget about derivatives, everything we know about derivatives before. Everything that applied before applies now.
X prime times 5 plus X.
Right, we need the product rule. I have two functions being multiplied. Now remember, the y is some function in disguise. I don't really know what this is. This y is some f of x, right? There's some blah, blah, blah definition packed into this thing. So it's a whole function by itself, right? So now I have x times another function, but it's still two functions multiplying, so I'm going to use the product rule. And what does that say? Well, I differentiate the x and I leave the y. 1 times y plus, now I leave the x and I differentiate the y, which is go y prime. Now, these two you might have missed something subtle, so let's unpack it. How do you differentiate y squared? 2y turns out you'd multiply by a y prime. Now, why would you multiply by a y prime? It's the chain rule is what you're using. Remember, your y is not just y. You're thinking of y as a function, right? So it's not like a y squared. It's like having f of x squared, right? Now, when you're differentiating that, you need the chain rule. You differentiate the outside, and then you multiply by the derivative of the inside, right? So every time I differentiate a y thing, I have to multiply by y prime because it's the chain rule. Because the y is not just a single variable y. There's a whole function there that I don't really know what the definition is. I just call it y, right? So there's really a whole lot of mess in here. It's not just an x. There could be a whole lot of stuff there, and I'm squaring all of it. Differentiate the outside, I get this. Then I have to multiply by the derivative of the inside. Yes?
So if X isn't a function?
No, x is just the variable. It's just the independent variable. Right? What about this one?
What's the half?
Right, you think of this as y to the 1/2. So do the power rule. So it's 1/2 y to the minus 1/2. And you multiply by y prime. So let's talk about the similarities and differences of implicit differentiation versus explicit differentiation, which we've been doing the whole time. Basically, how the process works is differentiate each term. As you usually would. You obey all the old derivative laws, they still apply. Right, so you can't forget things like the product rule, quotient rule, chain rule, power rule, they all still apply. Except, and here's what makes a difference. When you differentiate a y term, multiply by y prime. We can kind of generalize this exception though, in general. You differentiate a dependent variable, you need to multiply by its prime. Because a dependent variable represents a function. There's a whole rule that's packed into a dependent variable. So the chain rule applies. And you have to do that because that's what the chain rule says you have to do. And that is, in a nutshell, implicit differentiation. Differentiate as you normally would, obey all the other rules, which means if you have two things multiplying, you need the product rule. If you have two things dividing, you need the quotient rule. If you have one thing plugged into another, you need the chain rule. Except, whenever you differentiate the dependent variable, you need to multiply by its derivative, because the chain rule says we have to do that. So, an example. Find y prime. Let's say I told you x times y equals 1. Find y prime. And that one is pretty easy to do in two ways. So let's actually do that in two ways. Let's say you never heard of implicit differentiation. How would you have tackled that problem?
Quotient.
Right, you just solve for the y, which is actually no problem. Right, so I could have just do it the old way, the explicit way. Just solve for the y. I get y equals 1 over x. And so this means y prime equals negative 1 over x squared. Right, use the power rule. Rewrite that as x to the minus 1, do the power rule. Right? You could have also done it implicitly, right? Where you don't even bother solving for the y. So what you would do is you look at this and you think, oh, this is one function times another function. So I have to do the product rule. So I differentiate the x, leave the y, plus leave the x, differentiate the y, I get 1y prime. Then differentiate the 1, I get 0. And then I just literally solve for y prime after that. Now y prime is just this thing that I want to find, but now it's just like solving for that is like solving for it in algebra. So this guy I move to the other side. And then I divide by x. And I can think of that as the answer. Right? Now in this case, it's pretty easy to see that both of these answers are actually the same. Because my y is actually 1 over x. And if I put 1 over x here, I actually get that. Right? But this is just as valid an answer as that one. So that would be the implicit way. Now you might be wondering, why would I do it that way? It seems to make things more complicated. Well, if you have an example like this, you would do it that way. X squared plus y to the 7th is 2y plus 3. Now, as it turns out, it's actually impossible to solve for that for y. There's no way to get y by itself on one side of that function. So remember, I don't know if they actually told you that now, but once you pass power 5, there's no general formula that will give you the answer, right? So there's no quadratic formula for the 7th power. And in fact, there are very few of them we can solve, and this is not one of them, right? So this is a case, we're doing it in the method of step 1, in doing it the explicit way, it just wouldn't work. There's no way I can get this off of y here. But it still doesn't stop me from getting to y prime. So if someone asks me find the derivative, find y prime, I still can do it. What I'm going to do is differentiate each term following all the old rules I know. So derivative of x squared, 2x. It's the independent variable, so I'm not going to do anything. Don't worry about it. Move on to this thing. 7y to the 6. Now that's a dependent variable. I need to multiply by y prime, right? Anytime I differentiate a y, multiply by y prime. This one. So now I have an expression with y primes in it, and I want to find y prime. How do I get y prime? You need to isolate it. How do you isolate it? What do we do? First step. Right, so when you want to isolate a variable, the first thing you do is anything that doesn't have that variable, move it to the other side. So I'm going to minus the 2x. Now what? Now it's a common term. And now, just divide both sides like that. So I get my y prime is equal to minus 2x over 7y to the 6 minus 2. Now you might be bothered by the fact that there's a y in your answer. That seems kind of weird. But I assure you, that is just as valid an answer as we've had for any problem before, and it's actually just as useful. I can literally ask you anything I asked you before, and you can still figure it out. So for example, I could ask you, as part B of this problem, find the equation of the tangent line. I believe it's 2.1. Alright, so you'll notice here, if I actually plug in 1 for y and 2 for x, this actually works out and gives me the answer. But, so this is like my x, and that's the corresponding y value. How do I find the equation of the tangent line? What do I need for the equation of the tangent line? I need a slope and a point, right? Because it's a equation of a line, so I just need a slope and a point. So here's the question: how do I get to the slope? The first derivative tells me the slope. So this is a formula that gives me the slope. How do I take advantage of this formula? Well, I can plug in x, but notice that there's a y. It doesn't matter. I also know the y. So I just plug in two different numbers, right? So I'm plugging in two numbers now instead of one. That's the only difference, right? So instead, I'm going to have minus 2, my x is 2, over 7 times 1 to the 6 minus 2. So this is minus 4 over 5. And that's my slope. And this is the point. This is like my x1, y1. So now I know for my tangent line, I'm going to use y minus y1 equals mx minus x1. So I have y minus 1 is equal to m x minus x1. And that's my answer. That's my answer. So I can do anything I could have done before. The difference is now I'm plugging in two numbers instead of one. And sometimes this is just unavoidable because the original thing that I had to deal with is just, it's too complicated to get it in a nicer form. Well, why did you just start out with a nicer formula? Why are you messing with this, man? Turns out, a lot of things we figure it out like this, messy. Right? When you start getting higher in your chemistry and all that stuff, you're going to come up with these equations where your variables are going to be mixed up. You're going to have relationships between pressure and volume and all sorts of stuff where everything's like mixed up and you're like, oh my God, and someone say, how is the pressure changing at this temperature? And you're like, ah! This is how you do it. You don't freak out, you just do things implicitly. Right? Like, things don't always come to you nice and clean. Sometimes things come to you messy, but you still need to know how to deal with them. So, there's a point to all this. In fact, one of my examples I think I have from a chemical equation, van der Waals equation. There's the ideal gas law, which is not so bad. You can actually solve for anything, right? I had another example. That'll probably just cause needless confusion. Let's do a couple more examples. By the way, just for curiosity's sake, if you wanted to know what that guy looks like, actually do a graph. And we actually found the equation of the line was like here. I researched the graphs, so I might as well put it on the board. Okay, good. Let's do some more examples. Can I get rid of this? V is volume, P is pressure. It's an equation in chemistry. I don't think you'll see it in 103, but probably later. Let's go. How do we do this?
One.
So what do we use here?
Product rule.
Product rule, right? One function times another function. So product rule applies. Differentiate one, leave the other one, plus dx derivative of y is 1y prime plus Power rule again, right?
Yeah.
One times another one. So 6x
Y squared plus 3x squared 2y prime equal to 0.
Right. Differentiate as you normally would. The only difference is every time you differentiate a y term, multiply by y prime. That's it. And at the end of the day now, you have to solve for the y prime, which is going to take some algebra skills. How do I solve for that?
Isolated.
You isolate it. So everything that has it, you leave it on one side. Everything that doesn't have it, put it on the other side. So here I have this x, y prime. Let's cross it out so I know that I dealt with it already. Here I'm going to have a 6x squared y, y prime. Let's cross that out so I don't dealt with it. So this y, move to the other side, get minus y. This 6xy squared, move to the other side. Now what?
Factor out.
Now y prime is a common term, factor it out.
Divided.
And then divide both sides by this guy. And that's your y prime. Okay, now what? The quotient rule, I have one function divided by another function. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared minus the derivative of this. 3 times y prime over y. Remember that rule for ln? Derivative of ln of something is derivative of the thing over itself equals 7. Now how do I, this is a minus sign. How do I isolate my y primes? I probably wouldn't do that. I mean, it can work out in this case, but there are cases where something like that would just get you in trouble. You could get rid of the fraction, multiply both sides by y squared, sure. But probably in general, in a situation like this, I'd probably just split the fraction into 2 parts, right? So just take that part off and then move it over. But you could also just multiply both sides by y squared. So that's another trick you'd have learned in algebra. If you want to have an equation with fractions in it, you want to solve things, you can just multiply through by the LCD, and then you don't have fractions anymore. So now you can isolate this guy, which means this guy you move over. So I have minus x y prime minus 3y y prime equals 7y squared minus y. So my y prime would be 7y squared minus y divided by minus x minus 3y. What happens here? How to differentiate an exponential? Exponential, remember, is the derivative of the power times the original function. What's the derivative of the power? Derivative of x plus y. Okay, that was done. Now move on to the ln. Derivative of ln is what? Is that it? Times 1 plus y prime, derivative of this. Or it's the derivative of the thing over the thing itself. So it's 1 plus y prime divided by that equals derivative of 2 is 0. So now I need to solve for this. Yes?
What happened to the 2?
I'm differentiating everything. So derivative of 2 is 0. I just go through and I differentiate everything using my old rules. So I know derivative of e to anything is just the derivative of the power times the original function. Derivative of ln of something is the derivative of the thing over the thing itself. And of course I'm applying the chain rule and all that. Derivative of 2 is 0. At this point, the trick of multiplying through by the LCD, as I said, in general I wouldn't really think of things that way because I'm going to have to multiply by x plus y. I'm going to have to FOIL out, and getting the y prime out of that is going to be kind of nasty. So what I'll do is I'll just expand this and break that fraction into 2 parts. Right? So this gives me e to the x plus y prime e to the x plus y. Right? Just expand this. Here, a fraction can split across a numerator. So this is 1 over x plus y prime over x plus y. And so now I've isolated the terms that have the y prime. So I can bring all the other guys on the other side. So I have y prime e to the x plus y prime over x plus y equals, subtract this, subtract this, and then I can factor out a y prime and divide by what's left over. X minus e to the x plus y minus 1 over x plus y divided by e to the x plus y. Factor out the y prime from here, I would get e to the x plus y plus 1 over x plus y. Now at this point, if the complex fractions bother you, you could multiply top and bottom by the LCD to make it a little nicer, but that's not for now. Find dV/dP, the rate of change of the volume with respect to pressure. So as pressure increases by 1 unit, what happens to the volume? What do I do here? What rule do you use? Product of this times that. Right, there's an f times a g. Now I have to remember who is the dependent or the independent variable. Who's dependent here?
Bottom.
No, pressure. The guy that's on the bottom is the independent variable, right? The volume is the, so the v is like the y, the p is like the x. So the p is the guy that when you differentiate, you're not going to do anything, but when you differentiate the v, you're going to have to multiply by the v prime. Right? So now that we know that, let's actually jump into this. This is a product rule, so I'm going to differentiate the first term, leave the second term alone. The derivative of this, derivative of p is 1, plus derivative of this is going to be minus 10b to the minus 3 times dv dt. Leave that alone. Plus. Right, I just thought of this as 5b to the minus 2. I left that. Plus p plus 5 over v squared times, now I'm going to differentiate this guy, derivative of v is just 1 times dv dt. Derivative of that is 0, derivative of that is 0. So now I want to solve for this guy. How do I solve for that? You mean FOIL? I can expand these brackets to get this guy out in the open. So it's 1 times this, 1 times that. It's going to be this times v. And then this times that, which gives me a plus. Now I have 3 terms where the thing I want is present. There are these guys that don't have it, so I'm going to bring them to that side. So this means I have minus 10 to the minus 2 dv dt. Or you can write v prime if you know, if it's understood that p is the independent variable, plus 0.3 v to the minus 2 dv dt, plus v plus 5 over v squared equals 0.03 times v. I'm going to factor the dv dt out and then divide by all of that. So this is 0.03 minus v all over this plus 2 plus 5 over this squared. And that's your answer. one more example I want to do here in this section. This is kind of looking ahead to another topic we're going to do called related rates, but it uses implicit differentiation, so I can start to introduce it here. Called the folium of Descartes. It's a curve that looks like this. That's a curve and there's something skating along it. This passes through -2, -2. Right, so some particle moving along this thing. And here's the information I know. At 3,3. Y current is changing at a rate of -1 meters per second. How fast is the x coordinate changing at this point? So this could be a word problem. One of the things that should jump out at you here is the word rate. Rate is a very special word. Basically, rate means you're talking about how things are changing with respect to time. So whenever people are talking about rates, it means that time is the independent variable. So we can call it t, for example. So this means both x and y are dependent. In other words, I'm not just thinking of x as x. X is some function with t's in it. And y is not just y. Y is some function with t's in it. Right? They're both representative functions where t is the input. Which means in this equation here, both of these guys are dependent variables. Which means I'm differentiating with respect to t. Now if I differentiate the x with respect to t, I get what's called dx dt. That's the Leibniz notation. Or I can think of it as x prime of t. Right? And if I differentiate with respect to t, the y function, that gives me dy dt. The Leibniz notation, or I can think of that as y prime, and emphasizing that t is the input variable. Okay. Now, given all of that jazz, how do we start to figure this guy out? So x prime means rate at which x is changing. Y prime is the rate at which y is changing. in other words, what this problem told us, they gave us the equation, and they told me how fast the y coordinate is changing. In other words, what they just give me, what this information is this guy. They told me what y prime is at that point. Okay. So now I just want to figure out what is x prime at that point. They asked me how fast is the x change. So what I'm going to need to do, to get primes, I'm going to need to take derivatives. So I'm going to need to differentiate this. So how do I differentiate this?
3x x prime.
Times x prime. Now when I differentiate the x, I have to put a prime there because x is not the independent variable anymore. T is, right? X itself is a whole function that's packed into there, right? Plus here, 3y squared y prime. Or it's customary here to use like dx dt. But if you write prime, I won't care. But if you read it in your textbook and things like that, they'll use that notation typically here because they really want to emphasize that the t is your independent variable. How do I differentiate that? I need the product rule. One function times another function. So derivative of 6x. Derivative of x is 1 times x prime. Plus, you leave the 6, leave the y, plus, now you leave the 6x to differentiate the y, you get dy dt.
So is that y prime?
That's y prime, yes. Derivative of y is dy dt.
Okay.
And so now we look at what we know. First of all, I know I'm at the point 3, 3. So I know my x equals 3, my y equals 3. I also know that the y coordinate is changing at a rate of -1. So in other words, I also know that dy dt is -1. So now I have all that information, I can just plug into here and solve for the thing I want to find. This means I'm going to plug in 3 for x, and that would give me what? That would give me 27. Dx dt, I don't know what that is, so I'm writing that back. Plus, plug in 3 for y, I get 27. This should be a dy dt. Now dy dt, I know is -1 equals 6. Dx dt times y. Dx dt, I don't know what it is, but my y I know is 3. Plus, I know my x is 3, my dy dt is -1. So now what I have? I have 27 x prime minus 27 equals, this is 18 x prime minus 18. I want to solve for the x primes. Bring that over. What do I have? 9x prime. Bring that 27 over there. Equals 9. So x prime equals 1. In other words, x coordinate is changing at 1 meter per second. So when your y is decreasing by 1 meter per second, your x will actually be increasing, which basically means we're on this curve. It will be moving down and to the right. Right, so it's going to be twirling around that way. Right, so you can figure out what direction this thing is moving. But that's basically it. The x-coordinate is actually going to be increasing, means moving to the right. So that's the x-axis. The y-axis. Positive would mean up, negative would mean down. And that's actually time. So we actually finished the implicit differentiation. We'll do a lot more problems like this when we get to related rates, but that's just an example. implicit differentiation at work. So I'll see you guys next week. Oh, I didn't bring them. Email me a reminder. So, are you on to